So this is a natural class to follow our trip to the art museum. So what was the whole point of the art museum? It was trying to talk about perspectives, ways to look at things. You know, the issues artists had when they were struggling to convey something, some emotion, some image to the viewer. Why is this important? Well, we're a liberal arts college. You know, we should be seeing connections between the different disciplines, the whole student, all that bullshit. But more importantly, it actually matters for what we're doing. How many of you can really picture a four-dimensional surface? Exactly. And so we have to start playing tricks. Now, if you think about it, a lot of times when you can actually physically see something, you can use that to get some sense of what's going on. In complex analysis, in one variable, we can kind of play some games and be okay. When we start moving to several complex variables, the intuition becomes a lot harder, and it becomes very difficult to visualize what's going on. So what I want to do today is just give you the most briefest of introductions to several complex variables. Now, one of the nice things about teaching and recording my lectures is I can actually view my video from previous years. And I think when I taught this a few years ago, I asked people if they still remember the SAT stuff, you know, A is to B, as C is to, and then they give you 5 choices. Do you guys still have that? Or have they removed that from the SATs?
It's gone.
Yeah, okay, that's what they said 2 years ago, and I'm pretty sure they hadn't brought them back. What I want you to think about is what happened when we went from real analysis to complex analysis. What were the changes when we went to complex? So can someone give me some of the big changes that happened? Yes?
Differentiable implies analytic.
Good. So in complex, differentiable implies analytic. If we wanted to, we could put the arrow both ways, but the other direction is really not that big of a statement, because analytic just means you have a series expansion that converges, and you can differentiate within the radius of convergence. This is a big difference between real analysis and complex analysis, that the way the variables are packaged together. Why do we have this? Where does this come from? So the other reason I want to do several complex variables is it's a great way to do a crash course review of what we're doing. What do we do this semester? Why does this hold?
Oh, this was a consequence of Cauchy's theorem.
Consequence of Cauchy. And that's really what the need was. We had Cauchy's integral formula, which gave us an integral expansion. And what we had was this beautiful, f of z is 1 over 2 pi I, some nice closed integral about, some boundary curve gamma of f of zeta over zeta minus z d zeta. And here's z, and here's some nice boundary curve gamma. Okay. What's so wonderful about this is we take a function that's defined on the boundary, and then we extend it. And there's only one way to extend it. If you think about what's going on, what's surfacing in the background is what? What's really lurking in the background? We've already used Cauchy, so who else has to be?
Cauchy-Riemann.
Cauchy-Riemann. We have the Cauchy-Riemann equations. This weekend I actually reviewed a paper proving the Riemann hypothesis. Among other mistakes, they misspelled Riemann. Do not misspell Riemann, please. That will get me upset. Okay? The Cauchy-Riemann equations are satisfied by a holomorphic function. They express how the function, the real and imaginary parts are connected, what the derivatives are like. Think of it as this differential equations going on. We have some control, we have some specification on the boundary. There's a unique way of filling things in. We expand this out using the geometric series formula. If we want to expand it about some other point, we can write, zeta minus z as zeta minus z naught minus z minus z naught. Right? And then we can pull out a zeta minus z naught, 1 minus z naught over zeta minus z naught. And then we can expand this using the geometric series formula, and you see the series expansion popping out. So you want to get a sense of, what is the depth? Where do results like this come from? Okay? So this is what's going on in one variable. Why is it so special to be complex differentiable? Why is that so much more than being real differentiable of one variable? What do you get when you're complex differentiable that you don't get when you're just, yes?
The limit has to exist from every direction.
It has to exist from every direction. And so in real, this is, real one dimension. Limits of Bohr. In complex, something like this, all paths, converging to a point. When you have a function that's complex differentiable, you have so much more control. But you do still have some geometry issues. So one of the biggest is if we have a singularity. So let's say we have a function that blows up at 0. We have a singularity here. What do we get if we integrate around? So if we do and let's say that's the only singularity, 1 over 2 pi I integral, call this gamma, of f of z dz.
The residue?
The residue. So we'll just get the residue of f at 0 in this case. And so in all of what's going on here, it's basically the function 1 over that's controlling everything that goes on. Right, so now the question becomes, well, what happens if we extend to several variables? What should be the definition of complex differentiable? What should the properties be? Which formulas, which theorems do we expect to still hold? So now let's do several complex variables. So let's say we have z1, zn. Do I want to use z sub I to denote a generic z? Not in this class, right? Do not use I as a subscript ever in several complex variables. It's a recipe for disaster. Okay? So what should the definition of holomorphic be? Yes?
It has a Taylor series which converges in some ball.
Okay, so I think that's 3 on the list. Let me double check. No, I did not write them down, but alright.
Holomorphic.
Yeah, okay, that's 3. Okay, so you're basically just saying it's analytic. Probably, but okay. Yes.
Holomorphic in each variable independent.
It is holomorphic in each variable. And the second one is a little strange. Continuous in each and holomorphic in each separately. You ever heard the expression "Tefei"? The following are equivalent. One of these implying another is pretty straightforward.
So I'm a bit confused about 2 isn't.
Yes, exactly.
I mean, holomorphic
Yes.
implies continuous.
Yes.
Okay.
Yes. Some people like to just talk about this. It comes down to some technical assumptions when you're doing some integrals. It's sometimes useful to have explicitly put in. If you think back to what's going on in Calc 3, what does it mean for a function to be differentiable? It's not enough for the partials to exist. You want to have good tangent plane approximations. So sometimes it's convenient to just throw in something like this. But in terms of proving all this stuff, 2 implying 1 is not that bad. Okay. The more interesting ones are basically 1 and 3. So the question is, what kind of sets do we want to look at? Well, when we looked at things in one dimension, what kind of sets do we look at in one dimension? In one complex variable? I'm sorry?
Intervals.
Well, what's an interval in C?
Discs.
Disks. So in C, we look at this. And you can spell disk C either with a K or a C, doesn't matter. What is a disk? A disk, maybe we'll write a D, AR is going to be, let me just make sure I want to do it in the same order as I'm going to do here. In other words, did they want to do R first or second? Yes, okay. It's going to be the set of all Z in C, Z minus A is less than R. I can draw this. Not well, but I can draw something on that line. What would be the generalization of this in several variables?
Just balls, open balls.
So one possibility, in Cn, is open balls. So DAR would be the set of all Z in Cn, and then we would do maybe Z minus A less than R. There's another definition. It's called the polydisk. It's denoted delta AR, and it's the set of all Z in Cn where ZK minus AK is less than RK. What does the polydisk look like?
Cartesian product of discs.
Yeah, Cartesian product of disks. Try to visualize that. And so, I've given you a link, or I'll give you a link later today to some notes in several complex variables if you want, where they try to visualize this. This is an extremely hard thing to visualize, which means our geometric intuition is going to be very hard to reach. One of the ways they often do this is they look at plots of the absolute values. So maybe here's Z1 and here's Z2. And maybe the polydisk R is 2, 3. So what would that be? That means, and we'll take the point A to be 0, 0. And we'll plot the absolute value of Z1 and Z2. We'll just plot what region that corresponds to. Because if I were to try to plot the region in 4-dimensional space, good luck. So what would this region look like on this plot?
Square.
Almost. Two is not equal to 3. Rectangle. And so, because R is 2, so this would be 2, and that would be 3. And so you can see how this would compare versus the absolute value of Z1 squared plus the absolute value of Z2 squared, the disk. Maybe looking, or an ellipse looking something like this, sort of like the ball. With again, absolute value of Z2. So you get a little bit of a difference in shape. But again, a lot is being hidden when we start to write things like this. And this is the difficulty. How do you visualize what's going on? This is why I wanted to go to the art museum and I wanted to spend some time trying to think about how you can try to get a sense. You can manipulate everything formally. There's nothing wrong with manipulating things formally, but you then don't have the intuition of being able to look at something and see what's going on. Alright, so this is a very brief introduction to some of the terminology from complex analysis. What we want to do now is we want to see what carries over from one variable and what does not. So we already had a list of shocks from complex analysis that was just very different than real analysis. I think at the beginning of the semester, I listed, like 4 things that were very different in complex analysis that were not the case in real analysis. Does anybody remember 4 things different in C? From R? Remember those lists?
It was definitely differentiable implies infinitely differentiable.
Good. So holomorphic implies not just infinitely differentiable. I can't even remember if this was 2 points anymore. Implies infinitely differentiable. So if you're differentiable once, you're differentiable infinitely many times. Holomorphic implies analytic. I know at least one other thing we had that was a real shocker.
F-bounded and
Yep. Holomorphic plus bounded implies constant. And there was a 4th shock, but I can't remember what the 4th shock was anymore. This is at least enough of a shock. A holomorphic bounded function must be constant. We had a really nice consequence of this. What was the nice consequence of this?
Fundamental theorem of algebra.
Fundamental theorem of algebra. If you can prove a fundamental theorem, you're doing pretty well. So, very different behavior for functions of one complex variable to functions of just 2 real variables. The way they are bundled together matters. And we of course also have stuff like this. So what would you hope holds for several complex variables? Would you hope that one implies infinitely differentiable? Would you hope that holomorphic implies analytic? Would you hope that holomorphic plus bounded implies constant? Well, let's look at 1 and 2. We'll concentrate on 1 and 2 because I want to make sure we leave time for the SES. What was the key in proving holomorphic implies all of this stuff? What allowed us to get these wonderful results? It's on the board. The Cauchy integral formula. Right? There's a reason I'm kind of squishing this over here on the very little bit that I left a little bit over here, is I want to keep Cauchy's integral formula on the board as long as possible. This is one of the gems of complex analysis. When we prove, and I do promise I will get to the proof of the Laplace inversion formula, this is actually going to be one of the key ingredients. And this is how we actually get the inverse Laplace transform, is we're going to use the Cauchy integral formula. It is miraculous that we can write a function in terms of an integral. There were lots and lots of consequences of this. We would love an analog of this. Okay? Most of the time, life is not a democracy. It's not today either. I will let you vote, but your votes don't count. Okay? You can choose, do you want to look at open balls or polydiscs? Anybody want to vote for either as the fundamental object for several complex variables? Any thoughts as to which one might be better? Or if you don't know which one is better, which one do you think I want to use?
Polydiscs.
Yes. I'm not going to introduce polydiscs. I mean, I could, but I'm probably introducing polydiscs for a reason. You know, here's the natural generalization. Here's something else we could do. What should we do? What a surprise, it's the natural generalization. You're probably introducing polydiscs because polydisc is useful somehow. Why do you think polydiscs are useful?
If you fix the other variables, then you still have the full disk and the remaining one.
You have a full disk in the remaining one. And what can we do on a full disk? Cauchy's integral formula. So you can begin to sniff out now why the polydisk is so natural. If it's a polydisk, look at the boundary. Ooh, the boundary is a product of circles. In planes, involving just one variable, essentially. Oh, I'm back to complex analysis in one variable, where I have the Cauchy formula. I'm not even going to bother wasting time writing down the generalization of Cauchy's integral formula in several variables. It's essentially exactly what you would expect. What you would need to do is you would need to just write down, instead of f of zeta, we would now write f of, maybe zeta 1, zeta 2, zeta 3, up to zeta n, and down below what would we have?
Zeta 1 minus z, zeta 2
Zeta
minus
1 minus z1 times zeta 2 minus z2. So the generalization would be very straightforward. We would have n integrals here. We would have 1 over 2 pi t. It's so beautiful. Let's try. Let's generalize it. I'll write it down. Okay. We'll keep it as is, so you can just compare the differences. F of z1 through zn would be 1 over 2 pi I to the nth power, integral gamma 1, integral over gamma n, f zeta 1, zeta n, zeta minus z1, zeta minus zn, d zeta 1, d zeta n. Exactly as you would expect. And the proof is just multiple applications of the standard Cauchy formula. Well, then what would be the next step? This just gives us, an integral representation. Now we want analyticity. How would we get analyticity? We want to get some kind of power series expansion. What would we do?
Take derivatives.
We could take derivatives. And so now we would want to take the derivatives with respect to z1 through zn. We would have to justify passing the integration through. You can begin to see why we like assumptions about continuity of our function. Compact sets, we should be able to pass the derivative inside. Derivative starts hitting these, you start having these powers start increasing. So we can probably differentiate term by term and prove that whatever derivative we want exists exactly as before. And now what if we want the series expansion? What if we want more than just it's differentiable? What if we want that it's analytic? So that would give me the coefficients, but I want to then say that I can bundle them all together. How did we get analytic before? We used the geometric series formula and we expanded these. We do the same trick in each one of these. So far, it's really not that different. So you can get analytic. It's the same idea. And you just have to show that the series converges, that everything is fine. Okay. So what I want to do is I want to choose just one place where there may be a difference. Okay? And this is the notion of a domain of holomorphicity, or a holomorphy. Okay. So we all agree that open disks are not great in several complex variables, and polydisks are much better. Alright, so I want to make sure I give the correct definition of a domain of holomorphy, so I will write it down carefully. So domain of holomorphy. So we say we have an open U contained in Cn is a domain of holomorphy if there exists a holomorphic function on U such that for all W in the boundary of U, and each, I'm going to use a word I've never defined before, but you should be able to figure out each polyradius R, so that's just what we need for the thing, there is no holomorphic function on a polydisk about W with polyradius R, which equals on a component of the polydisk intersects U. I.e., in other words, we cannot get a holomorphic extension across a boundary point. Or across part of U's boundary. Okay. So basically, imagine, here's my set U. Here's some point. I'm going to just draw things in one dimension. I draw some little disk about that point. Here's the disk intersected with U. That'll be the little part in here. If I start off with some holomorphic function on F, I don't want to be able to construct a holomorphic function which is defined on a slightly larger set, which will agree with the original function. So a natural question to ask is, if I give you a set, is it a domain of holomorphy? So this all comes down to, when can you extend something? Does this remind you of anything we did earlier in the semester? We didn't spend too much time on it, but we did spend a little time on this topic. Where maybe something isn't defined, but then in the end we found out we could define it.
And there's a continuation.
I'm sorry?
I know it's a continuation.
It's a little bit different than, infinite continuation is definitely one thing it's related to, but there's also something else. So this is the removable singularities. And we saw that there were some nice consequences of being able to remove singularities. So you initially might have the function not defined, and this is extremely similar to the inlet continuation because you are continuing it. Typically we're doing this at just one point. So let's try to think of a really good set to study. We want a set with the simplest possible boundary set. I probably want there to be at least one boundary point. Right? Why do I want at least one boundary point?
You can't really do that.
If there's no boundary points, then what must you be? If you have an open set with no boundary points, the whole thing. And I've got a function that's holomorphic on the whole thing.
Or none of it.
Or none of it. Or it could be the empty set. And so it's really not interesting if I don't have a boundary point. Okay? I want a boundary point. So the simplest set I could study would be a set that has just one boundary point. What set has just one boundary point?
A 1 point set.
I'm sorry?
A 1 point set that's not open.
But it's not open. So I want an open set with just one boundary point.
Complex plane minus a plane.
Complex plane minus 4. So look at the punctured plane. So what we're going to do is we remove the origin, and we have everything else. So this is a really good example to look at. It's the simplest possible case. So an open is a domain of holomorphy if there exists a holomorphic function such that for each point I can't extend. Can you give me a function that I might have trouble extending?
1 over z.
Yeah. F of z equals 1 over z causes 20. So in one dimension, if I give you the punctured complex plane, I can find a function very easily that I can't extend. What if I give you the punctured disk? So now, the boundary's more interesting. clearly the function 1 over z is going to blow up. But the function 1 over z is well behaved everywhere on the boundary. So I don't want to go into all the epsilons and deltas. Can somebody give me a way to try to tweak this and cause problems? I need to cause problems at the boundary. If it's too hard to do the entire boundary, can you give me at least something that will have problems at least at one point on the boundary?
1 over z times z minus 1.
Okay, so now I could start multiplying or I could start adding. I think for this I'd rather add than multiply. And so I could have plus 1 over z minus 1. And what I'm going to do is I'm going to start maybe putting in problems at each point on the boundary. Well, there's uncountably many points. Okay, I can't do that. But maybe I can take a countable set. Maybe I look at all nth roots of unity. So, you often, e to the 2 pi I k over n. If you raise this to the nth power, this is going to be 1. Or another thing you could do is you could look at e to the 2 pi I xn, where xn ranges over all rational numbers. And that will give you a dense set on the boundary. And so maybe I could look at 1 over z plus a sum, and goes from 0 to infinity, of 1 over z minus e to the 2 pi I xn. And now, inside maybe it'll be well behaved and it's going to blow up on the boundary. What's the only problem with looking at a sum like this? It's an infinite sum. So as soon as you see an infinity, you should be afraid. What are we afraid of now? Convergence. What could we do to help? So this function is probably not going to converge. At least in the interior. What could we do to maybe help it converge? Weight it. So maybe we put in some factor, an. Maybe an is, n to the n to the n to the n to the n. Maybe put factorials on each one of these. Maybe put a factorial there as well, something like that. Put in a huge weight down below. Right? If I now take any point inside the disk, what I can do is I can look at the point on the boundary that's closest. That will give me the largest contribution of one of these. And as long as I'm in the interior now, I should be fine. As I start getting closer and closer and closer, yes, this is going to be getting larger and larger and larger, but it's going to be a finite number. For any z in the unit disk, it's going to be a finite number. I probably don't even need anything as strenuous as this. This is probably overkill. I like overkill. I don't have to worry. I'm safe with something like that. Maybe I would be fine with just 1 over 2 to the n, or 1 over n squared. Just use something that would give me a convergent sum. Maybe as long as the sum of the reciprocals of a n converges, I'm fine. Then the question becomes, will this blow up as I actually go to the boundary? And so I'll leave it to you to investigate something like this. Okay? But you can construct for any open set a function that's blowing up as you approach the boundary from any place. So in one complex variable, an open set is a domain of holomorphic. You will always be able to find a nice holomorphic function that you cannot extend anywhere. In several complex variables, it's different. You can construct a nice open set where you will always be able to extend functions. And so the punctured disk or an analog of this in several complex variables, you can actually extend. This should be very similar in spirit to the removable singularities. I don't want to go to the details of it. I want to just try my luck at asking you to recall something from Calc 3. Anybody remember Calc 3? What are the big theorems you're supposed to get at the end of Calc 3? There's 3 of them. They're all the same theorem. Stokes, Green's,
Divergence.
and Gauss's divergence. They're all the same theorem. So the way you write them all in common form is using differential forms. So this is the fundamental theorem of calculus, also called Stokes' theorem. So the integral of d omega over some c is equal to the integral over the boundary of c of some omega. And then all the different things you have, it's just what does it mean to take the derivative of different things, you get all the different stuff. The fundamental thing of calculus, think of this as your function big F. This would be big F of b minus big F of a. This is the boundary, here c is some nice interval ab. The boundary of c will be b and a, but we have to be careful about how we do the boundary. The derivative of f is little f, and this is the fundamental theorem of calculus. Green's theorem in a plane and Stokes' theorem in 3 dimensions are very similar, but there's a difference. If you have a singularity in the plane, and you have some nice boundary curve around it, you cannot contract this curve and miss this point. But imagine you're in 3 dimensions, what could you do?
Go around it.
How?
If it was a sphere, for example.
Yeah, if it's a sphere, you can start lifting it up. Or if you want, fix these 2 points over here and start folding this over and put it on here, and then you can start contracting it. That's essentially what I wanted. That was the punchline for today. Is to just give you a sense that as you go into higher dimensions, you have more freedom to move. That freedom to move has consequences. Just like there were consequences in 1 dimension. In 1 dimension, we have non-trivial closed curves in C. There are no non-trivial closed curves in the real line. It's boring. You go out, you come back. In the plane, you can go around in a circle. Okay. So this is the end of the very brief introduction to several complex variables.